on advanced manufacturing processes. Under this course, in this session, let us discuss about advanced solid state joining process. In the last session, we have discussed about the resistance welding process and few variants. We have seen the principles of the variant processes, their advantages, limitations and applications. Moving ahead, in this session, let us discuss the solid state welding processes, namely the ultrasonic welding process and explosive welding process. Let us see their process principles, advantages, features, materials suitable to be welded by these processes and potential applications. First of all, let us study ultrasonic welding process. Ultrasonic welding process is a solid state process in which coalescence is produced by the localized application of vibrations. The vibrations are of very high frequency in the order of 10,000 to 20,000 hertz, and they are of shear type which act on the surfaces that are held together under a light normal pressure. The next figure shows the basic components and the configuration used in ultrasonic welding process. The ultrasonic transducer is essentially the same as that of employed in ultrasonic machining. We have already discussed one session on ultrasonic machining, in which we have seen about the ultrasonic transducer as well, which is responsible for producing ultrasonic frequencies. So, this is the configuration used in ultrasonic welding process, which is a solid state process, in which this is the transducer which is responsible for producing the ultrasonics. These frequencies or the vibrations will be transmitted to the zone of importance through this sonotrod. The zone of interest means the workpieces to be joined are together, and there will be a light force applied onto them in addition to this ultrasonic vibrations. So, under the vibration which are of shearing in nature and this light pressure, the materials here in this zone where the sonotrod will concentrate the ultrasonic vibrations will get locally heated and get fused. The ultrasonic transducer is coupled to a force sensitive system that contains a welding tip on one end. The pieces to be welded are placed between this tip and a reflecting anvil, thereby effectively concentrating the vibration energy onto the zone of interest or where the welding is to be carried out. In this process, one can either adopt stationary tips for spot welding as in the spot welding, or use rotating discs for seam welds, which depends on the process and design requirements. Now, there are few process variations in this ultrasonic welding process. Basically, there are 4 variations. They are of this type. Number 1, ultrasonic spot welding, ultrasonic ring welding, ultrasonic line welding and ultrasonic continuous seam welding. Let us first of all discuss ultrasonic spot welding. In this configuration, individual welds are produced by momentary introduction of vibratory energy into the workpieces. The workpieces are held together under pressure between the sonotrod tip and the anvil face. The tip vibrates in a plane essentially parallel to the plane of the weld interface, which is perpendicular to the axis of the applied static force. Spot welds between sheets are roughly elliptical in shape at the interface. At the interface, the spot welds can either be overlapped or the distance between the successive spots are reduced to a very narrow space, thereby essentially producing a continuous weld joint. Now, let us move on to ring welding. It produces a closed loop weld which is usually circular in form, but may also be square, rectangular or oval. Here the sonotrod tip used is hollow and the tip face is contoured to the shape of the desired weld. Therefore, this means the sonotrod tip, suppose if this is the sonotrod being used, generally this sonotrod will be having a flat face like this, having the cross section like this. Now, in this case the sonotrod can have different shapes. It can be oval like this and it will be generally hollow, whereas this is entirely solid. Therefore, the seam or the welding will take place across this or along this solid portion only, wherever there is the solid portion is touching these plates. Say, let us consider these two plates are being touched by this sonotrod, then the welding will take place on an elliptical cross section or the seam, that is the shape resembles to the sonotrod shape, and this shape can be even square or some other configuration as the requirement or the workpiece shape demands. So, this is nothing but sonotrod, even this is, and this is the cross section of the sonotrod. This is the plates to be joined. The tip is vibrated in a torsion plane parallel to the weld interface. The weld is completed in a single weld cycle. Now, let us talk about line welding. It is a variation of spot welding in which the workpieces are clamped between an anvil and a linear sonotrod tip. The tip is oscillated parallel to the plane of the weld interface and perpendicular to both the weld line and the directions of applied static force. The result is a narrow linear weld which can be up to 150 millimeter in length produced in a single weld cycle. The next is continuous seam welding. It is a continuous process. In this process, joints are produced between workpieces that are passed between a rotating disc shaped sonot rod and a roller type flat anvil. The tip may traverse the work while it is supported on a fixed anvil, or the work may be moved between the tip and a counter rotating or transverse anvil. The advantages of this process are: ultrasonic welding has advantages over resistance spot welding, such that it requires very little heat application during joining without melting of the metal. Consequently, no cast nuggets or brittle intermetallics are formed in ultrasonic welded parts. There is normally no arc produced, and hence it does not have the tendency to expel molten metal from the joints. The process permits welding of thin to thick sections as well as joining a wide variety of dissimilar metals. The ultrasonic welding of aluminum, copper and high thermal conductivity metals requires substantially lesser energy as compared to resistance welding. As we have already discussed while discussing the resistance welding process, particularly in case of high electrically conductive material, since the resistance of the material is less, therefore, to compensate for resistance, one has to apply higher degree of current to generate the same amount of heat that is needed for melting and fusion of the material. However, no such conditions are prevalent in this type of technique, where it does not depend on the resistivity or conductivity of the work material. The pressures used in ultrasonic welding are much lower. This also another advantage of this process. Since the pressure requirement is less, therefore, the fixtures to be used need not be very complicated or very heavy in construction. The welding time is also much shorter relative to many other welding processes. The deformation thickness is significantly lower than other cold welding processes. Since the temperatures used are low and no arcing or current flow is involved, the process can be applied to heat sensitive electronic components with better efficiency. For many electronic components, it is essential that the components are not heated beyond a certain limit. Otherwise, the components inside can get damaged. Therefore, in such cases, some conventional thermal based welding techniques may not be suitable, in which the heat affected zone get wider and wider. However, in this process, ultrasonic welding process, which is essentially not a thermal process, but the heat is generated at a very localized portion, can be very useful for such components. Intermediate compounds seldom form, as there is no contamination of the weld and the surrounding areas. The equipment is simple and reliable, and only moderate operator skills are required to operate the electronically controlled ultrasonic setups. the required penetration is less than most competing processes, for example, resistance welding, and correspondingly lesser energy is needed to produce the welds. Now, let us identify few disadvantages of this process. Ultrasonic welding is restricted to the lap joint welding of thin sheets, foil and wires, and the attaching of thin sheets to heavier structural members. The maximum thickness of weld is about 2.5 millimeter for aluminum and about 1 millimeter for harder materials. Applications of this process include welding of bimetallic plates, welding of microcircuit electrical contacts, welding of refractory or reactive metals, bonding of ultra thin metals, and encapsulating explosives or chemicals. It is also possible to bond metals to non-metals such as aluminum to ceramic or glasses. This table as shown in the screen gives an idea about which are the materials compatible for making this ultrasonic welding. Say for example, aluminum can be welded to aluminum, aluminum can be welded to copper, germanium, gold, molybdenum, nickel, platinum, silicon, steel and zirconium. Similarly, copper can be welded to copper as can be seen here, not to aluminum or not to germanium, not to molybdenum, neither to silicon. Similarly, other metals like germanium, gold, molybdenum, nickel etc., are also shown against other materials to whom they can be welded using this particular process. The weldability of zirconium is found to be with aluminum, copper, then molybdenum, nickel and steel apart from itself. Now, let us move on to another non-conventional and advanced joining method or welding method, that is explosive welding method. This method, explosive welding, in short also known as EXW, is primarily used for bonding sheets or corrosion resistant metal to heavier plates of base metal, say for example, a cladding operation, particularly when large area are involved. On the other hand, we have seen spot welding or the ultrasonic welding are confined to a small, relatively small area. However, this explosive welding is more suited to larger area for bonding. Explosive welding as a solid state process was first established in the year 1944 while experimenting with metal discs using a detonator. From the year 1960 onwards, the process was exploited commercially worldwide. It was mainly used for cladding large areas of different metals. Let us note about the prerequisites for explosion welding process. Number 1, a small standoff distance is maintained between the surfaces that are to be joined by the explosion welding process. Number 2, the force imparted by the explosion will bring the surfaces to be joined together progressively. Number 3, the velocity of the collision should be lesser than that of the sound, otherwise the shock waves will interfere and prevent the formation of bond. In order to get the plastic deformation towards enabling a good weld joint, the pressure between interfaces at the collision must exceed the material's yield strength. Now, let us look at the process itself. The bottom sheet of the plate is positioned on a rigid base or anvil. The top sheet, which is to be welded to the bottom sheet, is inclined to it with a small open angle between the surfaces to be joined. An explosive material is usually made in the form of a sheet. It is placed on top of the 2 layers of metals. It is detonated in a progressive fashion beginning from the mating surfaces. Compressive stress waves of the order of thousands of megapascals sweep across the surfaces of the plates. This can be explained like this. Suppose this is the original plate on which another plate, say for example, this is to be welded. Now, this original plate of material like this is placed on a fixed anvil or a base, and this is the sheet is to be welded on this. Now, on top of this explosive will be placed in such a way that this can be detonated successively from one end to the other end. So, this is nothing but explosive, and this is the plate to be welded, and this is the base plate, and this is a rigid, we can say, anvil. So, this rigid anvil will be responsible for withstanding the explosive pressure that will be generated by these explosions. So, in initial configuration, this plate will be placed something like this, that is to some extent inclined on this, and then as this explosion takes place, this distance will be minimized, the shock wave will be, compressive stresses will be used, will be generated, and this will make this weld thin plate to get welded onto this base plate. So, as the successive explosions does take place, so this continuously this plate will come closer to this, and ultimately this will form the welded portion like this. The clean metal surfaces are then trussed together under high contact pressure. The result is a low temperature weld with an interface configuration consisting of a series of interlocking ripples. The bond strength obtained in this welding is quite high. The explosive clad plates can be subjected to a wide variety of subsequent processing. These processing include further reduction in thickness by rolling. In the solid state welding process, numerous combinations of dissimilar metals can be joined. So, this shows the basic configuration of this explosive welding process. This in the screen, as can be seen, this is the base metal and this is the another plate to be joined or welded onto this base plate. Now, the explosives will be placed on these two along the length of these plates. Now, continuously the explosions will be caused and because of this the compressive stresses will be developed and they will try to bring these two plates together under very high stress and this will cause a cold welding of these two surfaces and finally, this will form a joint like this. This joint can further be processed, like it can be rolled again, so that there will be better uniformity obtained or can be heat treated or and so on as per the requirement of the joint. The joint quality depends on the nature of the interface and the effect the process on the properties of the metal components. The properties of relevance include strength, toughness and ductility. Using standard ASTM procedures, the effect of welding on these properties can be determined. Further, the result of tension, impact, bending and fatigue tests of welded and unwelded materials can be compared. Now, let us note the benefits of explosive welding process over other processes. This process can be used to join dissimilar metals. Very high bond strengths can be achieved. Then the properties and strength as good as that of parent materials can be achieved. Large surface areas can be joined or welded. This is clearly another advantage, like two sheets of paper or two sheets of metal, mostly in the metal, if are to be joined, then the conventional processes it is very difficult or time consuming. However, by application of explosive welding process, they can be joined very easily at low cost. Even under hostile conditions, for example, war conditions where we may not have adequate equipment for other kind of welding, this joining technique can be readily used. The advantages of this process include it can bond many dissimilar or normally unweldable metals. Minimum jig and fixers are required in this process. The process is essentially very simple and extremely large surfaces can be bonded, which is clearly an advantage. Wide range of thicknesses can be explosively clad together. No effect on parent properties can be observed, because there is hardly any thermal effect involved on this, and therefore, the parent material properties remain intact, which is very significant, because we have already seen in few other processes where heat affected zones are formed. Then along with that heat affected zones, the material properties or the parent material properties get changed, which may not be desirable in many cases. And of course, the quantity of explosives required may not be very high. However, there are few limitations as well of the process. These limitations include the metals must have high impact resistance and ductility. Mostly the brittle materials cannot be joined in this process because they may get cracked. Therefore, ductility is a property which is considered almost prerequisite for this, for the materials to be joined using this process. Noise and blast can require operator protection, vacuum chambers, or the entire process should be carried out in a buried condition or under water condition. The use of explosives in industrial areas will be restricted by the noise and ground vibrations caused by the explosion. It can cause safety hazards. The geometries welded must be simple, generally a flat, cylindrical or conical geometries are possible in this process. Some intricate geometries may not be possible, or even if one gets it, the result may not be as per expected. Now, let us see different features and applications of this process, explosive welding process. In general, any metal can be explosion welded if it possesses sufficient strength and ductility to withstand the deformation required at the high velocities associated with the process. Metals that will crack when exposed to the shock associated with the detonation of explosives and collision cannot be explosion welded. Metal with elongations of at least 5 to 6% and Sharpie V notch impact strength of 13.6 or better can be welded by this process. Explosion welding does not produce change in bulk properties. It can produce some noticeable change in mechanical properties and hardness of metals. This happens particularly in the intermediate area of the weld interface. Commercially significant metals and alloys that can be joined by explosion welding are shown in this table. This is shown in the screen. Different materials like carbon steels, alloy steels, stainless steels, aluminum alloys, copper alloys, nickel alloys, titanium, tantalum, etc. are shown against the materials with whom they can be explosion welded. In most of the cases, they themselves can be welded. Say for example, titanium can be welded to tantalum and titanium itself. But in some cases, say for example, nickel alloys may not form a very good explosion welding joint with material like cobalt or columbium. So, therefore, few restrictions are there. Apart from these restrictions, most of the metals or alloys can be welded each other using this explosive welding process. Now, let us look at the product applications of this explosive welding process. Joining of pipes and tubes can be very easily carried out using this explosive welding process. Major areas of use of this method are heat exchanger tube seats and pressure vessels, tube plugging, remote joining in hazardous environments, joining of dissimilar metals, say for example, aluminum to steel, titanium alloys to chromium nickel steel, copper to stainless steel, tungsten to steel, etc., etc. Attaching cooling fans, this is another significant application. Other applications of explosive welding are chemical process vessels, which are essentially big ones, as we have already discussed. This process is particularly suitable for large area bondings or weldings. Shipbuilding industries, in which also large sheets are to be welded or joined together. Then in cryogenic industries, etc. Now, let us summarize what we have discussed in this particular session. In this session, we have discussed about the solid state welding processes, namely the ultrasonic and explosive welding processes. The principles of working of ultrasonic process and explosive welding processes have been discussed. Both are solid state processes, and both processes do not have much of the thermal fallouts. That is, in both the processes, heat affected zones are very limited. Applications and features of ultrasonic welding and its variant processes, namely the spot welding, line welding and continuous welding, have been discussed. The prerequisites and process features of explosion welding processes have been discussed, in which we have found ductility of the material is an important aspect for the materials to be explosion welded, and generally large area are preferred, and the advantages and limitations and applications of these processes, both the processes have been discussed. In both the cases, we have found that these processes are unconventional in nature, and to a great extent they are clean processes which do not burn any gases, do not produce any arcs, and generally do not produce any slags or debris, etc. And in both the cases, basically the energy used is of unconventional in nature. In the first case, electrical energy is used for producing the ultrasonic waves or the frequencies. In the later case, that is in the explosion welding, the energy is produced by means of exploding some explosives, which is designed as per the requirement of the welding process. We hope this session was informative. Thank you.